For 4 billion years, the moon has been a graveyard of silence. No wind, no rain, no sound of any kind. Because sound needs air to travel, and the moon has none. For 4 billion years, the only things that disturbed its surface were the occasional strike of a meteorite, the slow creep of temperature change between 2-week-long days and 2-week-long nights, and the relentless invisible rain of cosmic radiation pouring down from the sun and the galaxy beyond. That is all. 4 billion years of absolute undisturbed cosmic quiet. The footprints that 12 Apollo astronauts left in the lunar dust between 1969 and 1972 are still there. They have not moved a millimeter. They will be there in 1,000 years, in 1,000,000 years, essentially unchanged, because there is nothing on the moon to disturb them. The moon does not age things. The moon preserves them, locked in gray silence, under the black sky and the stars that never twinkle, because there is no atmosphere to make them do so. In 2033, that silence ends forever. NASA is not planning a visit. NASA is not planning another series of short missions where astronauts plant a flag, collect rocks for a week, and come home. What NASA announced in March of 2026, while 4 of their astronauts were in the middle of the first crewed lunar flyby in more than 50 years, is something categorically different from anything humanity has ever attempted. They are planning to move in, to build, to stay, to create a permanent human outpost at the south pole of the moon, a base with habitats and nuclear power plants and pressurized rovers, and the infrastructure for dozens of missions per year. A base designed not to be visited but to be inhabited. A base that, once operational, may never truly be empty again. The price tag announced is $20 billion over 7 years, with more to follow. The White House posted a message that read, "America will never give up the moon again." NASA Administrator Jared Isaacman, a man who has paid for his own trips to space out of his own pocket and who brought to the top job at NASA an energy that the agency has not felt since the Apollo era, said something that deserves to be quoted exactly. He said, "The goal is not flags and footprints. The goal is to go there and stay there." The year 2033 is significant for one reason, that most reporting on the moon base entirely misses. It is not primarily about the moon. It is about Mars. To understand why humans absolutely have to have a functioning base on the lunar surface by the early part of the 2033 window, you need to understand something about the geometry of the inner solar system and the narrow, irregular windows it opens for the most important journey our species will ever attempt. Mars and Earth orbit the Sun at different distances and at different speeds. Earth completes its orbit in 365 days. Mars takes 687 days, nearly 2 Earth years. Because of this difference in orbital period, the two planets are not always in the same relationship to each other. Sometimes they are on the same side of the Sun, relatively close. Sometimes they are on opposite sides, separated by hundreds of millions of kilometers. The alignment that creates the most favorable conditions for a crewed mission to Mars, the lowest energy trajectory that minimizes the amount of propellant needed and reduces the transit time as much as physics allows, occurs roughly every 26 months. These are cold launch windows and they are not flexible. You cannot choose a different alignment. The solar system runs on its own schedule. This 2033 window is especially favorable for a crewed mission to Mars. A functioning lunar base by then becomes the critical infrastructure that makes such a mission realistically possible. That competitor is China. And China has announced that it intends to land astronauts on the moon's surface by 2030. Same South Pole, same water ice deposits, same resources. The countries that establish operational infrastructure there first will not be able to legally claim the territory under the Outer Space Treaty of 1967, but they will be able to establish operating norms. They will be able to define what responsible operations in that region look like. They will be the ones with the water extraction equipment already in the ground when the legal arguments about who has access to what begin in earnest. Former NASA Associate Administrator Mike Gold put it directly in Senate testimony. The countries that get there first will write the rules of the road for what we can do on the moon. Getting to the south pole of the moon and building a permanent base there by 2033 is not just a scientific achievement, it is a strategic necessity. But the geopolitics, as urgent as they are, begin with something more fundamental. The thing that makes the moon so valuable, and the thing that makes it so hostile. The real reason humanity is going back to a world that seems, from the outside, to have nothing to offer is that the moon, it turns out, is hiding something extraordinary, and it is also trying to kill you every second of every day you spend there. When the Apollo astronauts returned from the moon between 1969 and 1972, they brought back 842 pounds of lunar rocks, a collection of samples that scientists are still actively studying more than half a century later. All 12 moonwalkers landed in the same general region of the moon, the equatorial near side, the flat, dark volcanic plains that are the most accessible and the least interesting geologically. This was the right choice for the Apollo program, which was a demonstration of capability more than an exploration of resources. But it meant that the most scientifically and strategically valuable region of the entire moon was untouched. The South Pole had never been visited, and the South Pole, as scientists slowly pieced together through decades of orbital surveys and robotic landers, contains something that changes everything. Water ice. Not water. Ice. Frozen, preserved, ancient ice, sitting in the floors of craters that have been in permanent shadow for billions of years. Craters whose floors are so cold that scientists believe the temperature there never rises above minus 250 degrees Celsius. To put that in human terms, the coldest natural temperature ever recorded on Earth's surface is around minus 90 degrees Celsius in Antarctica. The crater floors at the lunar South Pole are roughly 160 degrees colder than that. They are among the coldest naturally occurring places in the entire solar system, and into those frozen dark chambers over billions of years, a slow and patient process has been depositing water. Comets and asteroids carrying water struck the moon in their billions during the early solar system. Water molecules that landed in sunlit areas were destroyed almost immediately by solar radiation, but water molecules that migrated, hopping across the surface one molecule at a time, driven by thermal processes, into the permanently shattered craters never escaped. They accumulated. They froze. They stayed. India's Chandrayaan-1 spacecraft first confirmed the presence of water molecules on the moon in 2008, detecting them in orbital spectral measurements. In 2009, NASA deliberately crashed a small spacecraft called L-Cross into Cabeus crater near the South Pole and analyzed the debris plume. Water ice was directly detected. Subsequent missions have mapped hydrogen concentrations across the polar regions, providing indirect but compelling evidence of where the ice is thickest. The best estimates suggest the lunar South Pole contains billions of tons of water ice, though the exact distribution, depth, and concentration remain uncertain enough that the first missions to land there will have exploring these deposits as one of their primary scientific objectives. Water is not just water. In the context of space exploration, water is everything. Split a water molecule with electricity and you get two gases, hydrogen and oxygen. Combine hydrogen and oxygen in a rocket engine and you get one of the most energetically efficient propellants known to chemistry. The engines that powered the upper stages of Apollo's Saturn V rocket, the engines that sent astronauts toward the moon, burned liquid hydrogen and liquid oxygen. The engines that will power the spacecraft designed to carry the first humans to Mars also burn liquid hydrogen and liquid oxygen, or liquid methane and liquid oxygen. Every kilogram of propellant that currently has to be launched from Earth has to fight against Earth's gravity, which is the deepest and most energy-expensive gravity well in the inner solar system after the Sun itself. Getting 1 kilogram of anything from Earth's surface to low Earth orbit currently costs roughly $2,000 to $3,000, even with modern reusable rockets. Getting it all the way to Mars costs enormously more. But propellant manufactured at the lunar South Pole from local ice does not have to fight Earth's gravity at all. It is already in space. The moon's gravity is only 1/6 of Earth's. Launching from the moon requires dramatically less energy than launching from Earth. A spacecraft that departs from Mars from lunar orbit, fueled by propellant produced from lunar water ice, is fundamentally cheaper and more capable than one that has to carry all its fuel from the bottom of Earth's gravity well. The moon becomes a gas station at the edge of the inner solar system. And gas stations at the edge of the inner solar system change the economics of everything beyond them. This is why NASA Administrator Isaacman has called the lunar South Pole resources the oil of the 21st century. He meant it literally. In the 20th century, control of oil reserves determined which nations had geopolitical leverage, which economies grew, which military capabilities could be sustained. And the 21st century, as humanity expands beyond Earth, control of the water ice at the moon's south pole will play a comparable role in determining who can operate in deep space, who can afford to send missions to Mars, who can establish refueling infrastructure that makes the entire inner solar system economically accessible. The stakes are not abstract. They're as concrete as the ice itself, frozen in the dark at the bottom of craters that no human being has ever entered. There is a second resource at the moon's south pole that is less understood but potentially even more valuable, and this one has no equivalent anywhere on Earth. It is called helium-3, and it is perhaps the most remarkable substance in the solar system. Helium-3 is an isotope of helium with 2 protons and 1 neutron, where ordinary helium-4 has 2 protons and 2 neutrons. The difference of 1 neutron changes its nuclear properties in a way that matters enormously. On Earth, helium-3 is extraordinarily rare. All of Earth's production comes primarily from the slow radioactive decay of tritium in nuclear weapons stockpiles. Earth produces somewhere between 8,000 and 10,000 liters of helium-3 per year. For comparison, a standard bathtub holds roughly 300 liters of water. The entire annual global production of helium-3 would fill about 30 bathtubs. It is so rare that its current market price is approximately $20 million per kilogram, making it by far the most valuable substance per unit of mass that humans have ever seriously considered extracting from anywhere. The moon, by contrast, has been accumulating helium-3 for billions of years. The solar wind, the constant stream of charged particles that flows outward from the sun, carries helium-3. Earth's magnetic field deflects most of it away before it can reach the surface. The moon has no magnetic field and no atmosphere. Every helium-3 particle in the solar wind that reaches the lunar surface simply embeds itself in the top few meters of lunar regolith. where it has been accumulating since the moon formed 4.5 billion years ago. Estimates of the total helium-3 reserves on the moon vary between roughly 650,000 tons and 3 million tons. The entire annual energy consumption of the United States could theoretically be provided by burning about 25 tons of helium-3 in a fusion reactor. The moon's total reserves could power human civilization for thousands of years. But there is a crucial qualification attached to all of this: helium-3 fusion. The process of fusing helium-3 with deuterium to produce energy is not currently a working technology. Fusion power of any kind is not yet commercially operational. The National Ignition Facility achieved fusion ignition, producing more energy than the laser energy delivered to the fuel in December of 2022. But that was a proof of concept involving tremendous laser infrastructure, not a design that could be scaled into a power plant. Commercial fusion, if and when it arrives, may or may not use helium-3 as its fuel. The physics of helium-3 fusion is genuinely attractive. The reaction produces charged particles rather than neutrons, which means far less radioactive waste and potentially direct conversion of fusion energy to electricity. But the engineering challenge of achieving helium-3 fusion at net positive energy is enormous and unresolved. The value of lunar helium-3 is real and it is high. Whether that value will ever be fully realized depends on whether fusion technology matures in the coming decades. What is not speculative is the near-term commercial market. Helium-3 is used right now, today, in medical imaging, in quantum computing, and in neutron detection for nuclear security. The company Interloon, founded by Rob Meyerson, a former head of Blue Origin, has signed contracts with the U.S. Department of Energy for the purchase of lunar helium-3, with planned delivery beginning in 2029. Helsinki-based cryogenics firm Blueforce has signed an agreement to purchase up to 10,000 liters of lunar helium-3 annually once extraction begins, a deal potentially worth $300 million. The first nation with operational helium-3 extraction on the moon will have a resource with current market value of $20 million per kilogram, and a long-term strategic importance that may dwarf any resource previously controlled by any nation on Earth. So this is the hidden reason for the 2033 base. Not just science, not just national prestige, water ice for rocket fuel and helium-3 for energy and technology. Resources that, once controlled, define who can operate in the space economy of the coming century. The moon is not a graveyard. The moon is a vault, and humanity is racing to be the first one through the door. But the moon is not only hiding valuable resources, it is also dangerous. Its greatest everyday enemy is the sharp, electrostatic lunar dust. For short missions, the dust was manageable. For a permanent base, it becomes a serious long-term threat to equipment and human health. That is why the long-term plan almost certainly involves going underground. As of April of 2026, 4 NASA astronauts are heading back from the moon's vicinity on the Artemis II mission, the first time any human being has been in the vicinity of the moon since December of 1972. The mission is a flyby. The crew will not land, but what they are collecting during their 10 days in space, the life support data, the radiation exposure readings, the physiological measurements, the communication system tests, the precision navigation data, the performance characteristics of the Orion spacecraft in the actual deep space radiation environment, rather than the simulated one in Earth orbit. All of that data will feed directly into the GAN designs of the missions that follow. Artemis III, planned for mid-2027, will test the commercial lunar landers in low Earth orbit, not at the moon, in Earth orbit where problems can be fixed and where rescue is possible if something goes catastrophically wrong. This is the lesson of Apollo 9, the mission in March of 1969 that tested the lunar module in Earth orbit for the first time before anyone committed it to actual lunar operations. NASA learned from Apollo that you do not skip steps. You validate systems progressively. Every step has to work before you take the next one. Artemis 4, targeted for early 2028, will be the first crewed landing at the lunar South Pole. 2 astronauts will descend to the surface in either a SpaceX Starship human landing system or a Blue Origin Blue Moon lander, depending on which is ready first. They will spend approximately 1 week on the surface. 4 spacewalks are planned. They will sample the soil, map the terrain, test the dust environment, begin characterizing the specific landing site for future infrastructure. They will be the first humans to stand in the most geologically ancient and resource-rich accessible terrain on the moon. They will look out across a landscape that has not changed significantly since before multicellular life appeared on Earth. Artemis 5, late 2028, begins the construction phase. From there, NASA's plan calls for at least 2 crewed landings per year, each one building on the last, each one leaving more infrastructure behind. The phase plan, presented to NASA contractors in March of 2026 and funded with $20 billion over 7 years, moves through 3 phases. Phase 1 runs through 2028 and focuses on establishing reliable, high-rate access, satellites for communication and navigation in lunar orbit, drones and terrain vehicles to scout the terrain, the first crewed landings to select and begin preparing the actual base site. Phase 2 runs from 2029 to 2032 and begins building the actual infrastructure, power systems, communication networks, surface mobility, and the first simple habitats. By 2032, NASA hopes to achieve the same level of continuous human presence on the moon that it has maintained for 25 years on the International Space Station. Not the same number of people and not the same comfort level, but the same fundamental model. Humans present, continuously, doing real work. Phase 3 begins in 2033. This is the phase where 150,000 kilograms of equipment and material arrives at the south pole of the moon in support of what NASA calls long-duration and long-distance human exploration. This is the phase where the first true habitats with full environmental control and life support systems arrive. Not camping equipment, not pressurized tents. Habitats, structures designed to keep people alive, healthy, and productive for months at a time, with airlocks and water recycling and air purification and radiation shielding and all the other systems that distinguish a building where people live from a vehicle they are passing through. In 2033, the Graveyard of Silence gets its first permanent residence. But here is the detail that takes your breath away a little when you really sit with it. NASA is not planning to build on the surface of the South Pole. Building on the surface of the moon means building in a place where the temperature swings more than 300 degrees Celsius over the course of a lunar day. It means building in a place where every structure, every solar panel, every antenna, and every rover sits exposed to the unshielded radiation environment of deep space. The Van Allen belts that protect Earth from the most energetic solar and cosmic particles do not extend to the moon. The atmosphere that blocks solar ultraviolet and X-rays on Earth does not exist on the moon. A person standing unprotected on the surface of the moon during a major solar particle event, a burst of high-energy particles from a solar flare, would receive a radiation dose equivalent to roughly the maximum allowable lifetime dose for a radiation worker in a matter of hours. The surface of the moon is, in radiation terms, a slow killer. The long-term plan for the Artemis base almost certainly goes underground, and the reason why connects directly to something the moon has been hiding beneath its surface for 4 billion years. There is a thought experiment that engineers at NASA's Johnson Space Center apparently use when they need to remind themselves of the true scale of what they are building. They ask, imagine you are going to construct a small town, not a city, a town, a cluster of buildings capable of housing a few dozen people, keeping them warm, keeping them fed, keeping them breathing, keeping them connected to the outside world, keeping their equipment running, keeping their medical needs met. On Earth, building such a town from scratch takes years and costs hundreds of millions of dollars. Even with roads to deliver materials, factories to manufacture components, hospitals nearby in case something goes wrong, workers who can go home at night. Now imagine all of that, except the nearest road is 240,000 miles away. Except there is no air. Except the temperature at the construction site swings between positive 130 degrees Celsius and negative 170 degrees Celsius, depending on whether the sun is up or down. Except the soil is made of microscopic glass shards that destroy everything they touch. Except every kilogram of building material that you bring from home costs more per kilogram than gold by the time it arrives. Except if anyone's spacesuit seal fails while they are working outside, they are dead before anyone can reach them. And now, build it. That is the assignment. That is what the Artemis base requires. And the most extraordinary thing about it, the thing that separates the 2033 plan from every previous vision of a lunar base that human beings have produced over the last 60 years, is not the ambition. It is the engineering honesty. Because the engineers who are actually designing this base are not pretending that the moon is manageable. They are designing around its hostility. They are not trying to bring Earth to the moon. They are trying to build something that could only exist on the moon, built from what the moon provides, powered by what the moon allows, and hidden in the places where the moon's own ancient geology offers some protection from the things that would otherwise kill you. The first thing you need to understand about building on the moon is that you essentially cannot bring your building materials with you. This seems obvious when you say it out loud. The moon is 240,000 miles away from the nearest hardware store. Launching things from Earth's surface to the moon costs, depending on which rocket you use, somewhere between $4,000 and $40,000 per kilogram. A single metal I-beam of the kind used in commercial construction weighs about 60 kilograms. At the lower end of that cost estimate, that one beam costs $240,000 just to get to the moon, before anyone has done anything with it. A conventional construction project uses thousands of tons of steel, concrete, glass, and copper. The number you get when you multiply that mass by the cost per kilogram of getting it from Earth to the lunar surface is a number large enough to make the entire global economy look like pocket change. You cannot build a permanent base on the moon by shipping building materials from Earth. The physics will not allow it. The only option is to build with what is already there. And what is already there, an effectively unlimited quantity, is regolith, the same material that destroys equipment and attacks human lungs, and yet simultaneously the only raw material available for construction. The moon's surface is covered in it, sometimes to depths of several meters or more, billions of tons of it sitting there waiting. The question is whether you can turn it into something useful, and the answer, arrived at after decades of laboratory research and increasingly sophisticated robotic testing, is yes. But the process of doing so is unlike anything previously attempted in the history of construction. It is called in situ resource utilization, or ISRU, and it is one of the most important words in the vocabulary of deep space exploration. In situ means in place. Resource utilization means making use of what you find where you are. The concept is simple. The execution is not. But NASA and its commercial partners have been developing the specific techniques for processing lunar regolith into useful construction materials for years, and by the middle of the 2026 program, several of these techniques have advanced from laboratory curiosity to testable technology. The most mature approach is called sintering. Regolith, when heated to temperatures between 900 and 100 degrees Celsius, partially melts and then recrystallizes into a solid material as it cools. The result is a glassy, gray, stone-like substance with physical properties that are, depending on how you process it, comparable to weak concrete or strong ceramic. It does not require water. It does not require chemical additives. You heat the dust fuses, you let it cool, and you have a building block. The energy required to do this can come from concentrated solar power, a lens or mirror array that focuses sunlight onto a target area, a technique that works well in the sunlit highlands around the lunar South Pole where the Artemis base will be located. The second, more sophisticated approach combines sintering with additive manufacturing. This is the approach most commonly described as three-dimensional printing with moon dust, and while that description is technically accurate, it undersells both the complexity and the elegance of what the technology actually does. A robotic system equipped with a printing head can move across the lunar surface and deposit layer after layer of sintered regolith, building up a structure from the ground upward, precisely, following a design that was programmed into it on Earth without any human being present. The system does not need to be supervised in real time, because the communications delay between Earth and the Moon ranges from 1 to 3 seconds, which is manageable for most operations. It works at night if it is powered by stored energy. It does not care about the temperature. It does not need to breathe, and it can work for months before the first human astronaut arrives, so that when the crew finally lands, there is already something waiting for them. The European Space Agency, working with architectural firms Skidmore, Owings and Merrill, has produced detailed conceptual designs for what a regolith printed lunar base would actually look like. The designs are not what science fiction has been selling for decades. There are no gleaming white domes, no transparent observation bubbles with panoramic views of the lunar landscape, no angular modernist architecture of the kind that looks beautiful in concept art. What the design actually calls for looks, in architectural terms, something between an igloo and a termite mound. The structures would be roughly dome-shaped to distribute the stress of internal pressure evenly in all directions, but their outer surface would be irregular, heavily textured, built up from layers of sintered regolith in a way that traps and holds more regolith against the outer shell over time, increasing the radiation shielding passively as the base ages. From the outside, an Artemis base habitat printed from lunar regolith would look, in the words of one of the architects involved, like a prehistoric cave system that had been grown rather than built, gray, dense, organic-looking in its irregularity, completely alien in context and yet somehow completely at home on the gray, blasted surface of the moon. Inside, the structure would be under positive air pressure, maintained by life support systems, and the walls, 3 to 5 meters thick depending on the specific design, would provide both mechanical rigidity and radiation shielding. A wall of solid sintered regolith 3 meters thick reduces the radiation dose inside by roughly a factor of 10, compared to the unshielded lunar surface. That is not zero radiation, but it is within the range that humans can tolerate for extended periods without immediate health consequences. The floor would be sealed and elevated slightly above the lunar surface to allow for maintenance access to the infrastructure underneath. The overall footprint of a single habitat unit is not large, perhaps comparable to a small house by Earth standards, but the life support systems, equipment storage, and workspaces mean that the usable living area for a crew of 4 to 6 is more comparable to a large recreational vehicle, comfortable by the standards of people who have chosen to live on another world for months at a time. Crammed by the standards of anything on Earth, but regolith printed surface habitats are not the long-term plan. They are what gets humans through the first years of lunar operations, the years when continuous presence is being established, when the systems are being tested, when the infrastructure is being built up. They are the buildings you put up before you find the city that was already there, because beneath the south polar region of the moon, geologists believe there are spaces that make every surface habitat humanity has ever designed look small. Think for a moment about the moon as it was 4 billion years ago. Young, still geologically active, its interior hot enough that vast quantities of magma pooled beneath its surface, periodically erupting through volcanic vents and flooding the low-lying plains with lava. As this lava flowed across the surface, it cooled from the outside in. The top of a lava flow, exposed to the vacuum of space, radiates heat very efficiently and solidifies quickly. The bottom of the flow, insulated by the already cooling rock around it, stays liquid longer. But the hot lava underneath, under pressure, keeps moving. It flows outward through channels and tubes, draining out from under the hardened crust above like water emptying from a pipe. Eventually, the lava drains out completely. The volcanic activity subsides, and what remains is an empty tube of hardened rock, still sealed by the layer of solidified lava above it, buried under subsequent regolith deposits, invisible from the surface but structurally intact. These are lava tubes, and on Earth they are impressive but modest features, typically a few meters to perhaps 20 meters in diameter. The largest known terrestrial lava tube being the Kazumura Cave System in Hawaii, nearly 66 kilometers long but only about 1.5 meters wide in most sections. The moon's lava tubes are different in a way that takes careful rereading to believe. Because the moon's gravity is only 1/6 of Earth's, the structural requirements for a lava tube to remain intact are dramatically lower. A tube that would collapse under its own weight on Earth can remain stable on the moon at sizes that are, by any reasonable measure, staggering. Gravity-sensitive mapping by the G-Rail mission, a pair of spacecraft that mapped the moon's gravitational field in exquisite detail between 2011 and 2012, revealed subsurface mass deficits in the lunar maria that are consistent with intact lava tubes more than 1 kilometer wide. 1 kilometer wide. For context, the Channel Tunnel connecting England to France is just over 7 meters wide. The Goddard Base Tunnel, the longest railway tunnel in the world, is about 9 meters in diameter. The lava tubes beneath the surface of the moon may be more than 100 times wider than the largest tunnels humans have ever built on Earth, and they may extend for hundreds of kilometers. NASA's Lunar Reconnaissance Orbiter has imaged what are almost certainly entrances to some of these tubes, pit craters, circular holes in the lunar surface where the roof of a lava tube has collapsed, exposing the empty space beneath. One of the most studied of these pits, located in the Marius Hills region, is roughly 65 meters wide and has been photographed with side-looking cameras that reveal a substantially larger cavern below the pit entrance, with what appears to be a horizontal floor suggesting the ceiling has not completely collapsed. The photographs show a place of extraordinary strangeness. The sharp circular edge of the pit, the abrupt transition from the gray sunlit surface to the absolute darkness below, a darkness that the cameras can barely penetrate even with their most sensitive settings. Somewhere below that edge is a space that no instrument has fully mapped, no human eye has ever seen, and no human being has ever entered. Inside a sealed lava tube, several things are true simultaneously. The temperature is constant. The lunar surface temperature fluctuates by more than 300 degrees Celsius between day and night. Inside a lava tube, insulated by meters of rock on every side, the temperature is stable at roughly -20 degrees Celsius, cold by any human standard, but the kind of cold that can be managed with insulation and heating. It does not fluctuate. The walls do not contract and expand with thermal cycling. The seals on pressurized structures do not face the constant thermal stress that surface structures must endure. Radiation inside a lava tube approaches zero. The rock above you, whether 5 meters or 50 meters thick, depending on the tube location and depth, blocks the galactic, cosmic rays and solar particle events that would otherwise penetrate any surface structure not encased in enormous masses of shielding material. The roof of a lava tube does not require any manufactured shielding at all. Nature built it 4 billion years ago. The pressure environment inside a sealed and pressurized lava tube is potentially dramatic. Rather than small pressurized habitat modules connected by airlocks, a sufficiently large lava tube could in principle be sealed at its entrances with pressurized barriers and then pressurized as a single vast enclosed space, creating not a habitat module, but something closer to an entire pressurized environment, within which people could work without suits, move freely between work areas, and live in something more closely resembling a small enclosed town than a spacecraft. This is not near-term. The engineering challenges of sealing a kilometer-wide tube entrance are substantial, and the long-term stability of lava tube structures has not been confirmed by any direct measurement. But the vision is real, and it is part of why several serious scientific proposals have called for reconnaissance missions specifically designed to enter and characterize lunar lava tubes before the permanent base is sighted. A 2025 study by researchers at the University of Trento, analyzing thermal data from the Lunar Reconnaissance Orbiter, identified a region inside one of the Marias Hills pits where the temperature appears to remain near 17 degrees Celsius, a result that has not yet been independently confirmed but that, if accurate, would represent one of the most remarkable discoveries in planetary science. A naturally occurring space on the moon where the temperature is comparable to a mild spring day on Earth, protected from radiation, hidden beneath the surface, waiting. The moon, it turns out, may have been preparing for us all along. The practical roadmap for how the Artemis base transitions from surface habitats to subsurface lava tube occupation is not fully mapped out. NASA's official published plans describe the early phases in terms of surface infrastructure, for the straightforward reason that surface infrastructure can be planned with information we already have, while lava tube habitation requires direct reconnaissance that has not yet occurred. What is built into the plan is a commitment to robotic scouting of the South Polar region during Phase 1, including specifically the investigation of subsurface voids and pit craters within operational range of the base site. The drones and rovers that arrive before the first human crew have mapped South Polar pit craters on their mission objectives list. The question whether the permanent habitation of the Artemis base ends up on the surface or below it may be answered within the next 3 years, as robotic explorers work their way across terrain no human has ever seen. But whether the base ends up in a regolith-printed dome on the surface, or inside a cathedral-sized lava tube buried beneath it, one fundamental challenge remains the same and cannot be avoided. It does not matter where you are on the moon. At some point during every 47-day lunar cycle, the sun goes away for 14 days, and when it does, every solar panel on the moon goes dark. This is the engineering problem that, more than any other, determined the specific location of the Artemis base, and the solution to it is one of the most consequential technological decisions in the history of the program. The lunar South Pole, like Earth's South Pole but in a more extreme form, has regions that experience nearly continuous sunlight because of the moon's very slight axial tilt relative to the ecliptic plane. The moon's axis is tilted just 1.5 degrees compared to Earth's 23.5-degree tilt. This means that at the poles, certain elevated ridges and crater rims experience sunlight for nearly the entire lunar year, with shadows only during brief periods. The Shackleton crater rim near the South Pole receives sunlight for more than 80% of the lunar year. Other high points nearby receive even more. A strategically placed solar array located on one of these high ridges could generate power for the vast majority of a lunar year without the fuel and maintenance costs of any other energy source. For the first years of the Artemis base, this near-continuous solar power is the primary energy source. The initial power systems planned for the South Pole base are solar arrays deployed on masts tall enough to keep the panels in sunlight even as the sun tracks low across the horizon. NASA's power architecture for Phase 2 anticipates roughly 10 kilowatts of continuous power from solar sources, enough to run basic life support, communications, and scientific equipment. 10 kilowatts sounds modest. By comparison, a typical American house uses about 1.25 kilowatts on average. 10 kilowatts is a reasonable start for a small outpost with minimal crew, but here is the fundamental limitation that makes solar power insufficient as a permanent solution. Even at the best South Pole sites, solar availability is not 100%. The moon's slight axial wobble, combined with the precise geometry of crater rims and local terrain, means that every location on the lunar surface experiences some period of darkness. For a permanent base designed to operate for years without resupply missions, a solar array that goes dark for days or weeks is not acceptable. You cannot turn off a life support system because the sun is at a bad angle. You cannot pause the water extraction operations because you have run out of electricity. You need power that does not depend on whether the sun is shining. You need power that will be there at midnight on the moon just as reliably as at noon. You need something that has, in the vocabulary of power engineering, a very high capacity factor, meaning the percentage of time it operates at full rated capacity, and baseload power, meaning power that can be counted on at any hour regardless of weather or season. There is only one power source that meets both of those requirements, and that can be delivered to the lunar surface in the near term. It is fission, nuclear fission, the same physical process that powers nuclear reactors on Earth, and that has been powering spacecraft since the earliest days of the space age. And NASA has been developing a specific implementation of this technology for the moon for over a decade. It is called the Fission Surface Power Project. And by the time you have finished reading this paragraph, the hardware that will power the 2033 Artemis base already exists in prototype form, has been tested in vacuum chambers at Glenn Research Center and at the Nevada National Security Site, and is closer to flight-ready than any nuclear reactor designed for planetary surface operation has ever been. The design is deliberately modest by nuclear power standards. NASA is not building the moon a conventional nuclear power plant. What the fission surface power system provides is roughly 40 kilowatts of electrical power, a number that sounds small in Earth terms but is transformative on the moon, from a reactor small enough to fit in the back of a pickup truck with a mass of approximately 3,000 kilograms, using highly enriched uranium fuel, and built with an expected operational lifetime of at least 10 years without refueling. The reactor core itself, once it arrives on the moon, is lowered into a shallow excavation in the regolith, covered with the ubiquitous lunar dust, and that layer of dust becomes, in this one application, a useful radiation shield. The reactor is not in the habitat. It is not in the crew's living area. It is a small metal cylinder buried in the moon, a kilometer or more away from the inhabited zones, connected by power cables and generating electricity that flows to the base without any exhaust, without any noise, without any moving parts except the Stirling engine converters that translate heat into electricity. 40 kilowatts. To put this in terms that translate, 40 kilowatts can power the life support, water extraction, communications, scientific operations, heating, and lighting for a crew of 4 to 8 people, plus their equipment continuously without interruption for as long as the fuel holds. 10 years of fuel at current design specifications. The nuclear reactor buried in the lunar regolith a kilometer from the Artemis base will still be generating electricity when its first crew has long since returned home and been replaced by the second and third and fourth rotations of people who will live there. It will outlast the base's construction phase. It will outlast the period when the base is still being proven out. It will hum quietly in the dark of the 14-day lunar night, in the silence of the South Polar crater rim, maintaining the electrical heartbeat of the first permanent human settlement beyond Earth. The Fission Surface Power Project completed its initial technology development phase in 2023. A contract for flight system development was awarded to Lockheed Martin in 2024. The project timeline calls for a demonstration unit on the lunar surface by 2028 as part of Artemis Phase 2. If that demonstration succeeds, and the engineering team is cautiously confident that it will, then by 2032, the Artemis base has reliable, continuous nuclear baseload power and the full capacity to sustain permanent human habitation. Add to that the water ice extraction operations that will be feeding hydrogen and oxygen into fuel storage facilities, and by 2033, you have something that has never existed in human history, an off-world outpost that is not dependent on Earth for energy or propellant. An outpost that is, in the most literal physical sense, self-sustaining, but the reactor and the habitats and the water ice extraction and even the lava tubes are all in some sense local. They are the base itself. They are what keeps people alive on the surface, the thing that keeps the base connected to the rest of humanity. The thing that makes the difference between an outpost and an island is something else entirely. It is a structure in space, not on the ground. It is a structure so alone in the universe that the people who designed it have taken to calling it, with affection and a little melancholy, the loneliest lighthouse in the universe. It is called the Gateway. The Lunar Gateway is a small space station in a highly elliptical lunar orbit called a near-rectilinear halo orbit, a figure-8-shaped path that swings close to the moon's south pole every week or so, and then arcs far out into space before returning. Unlike the International Space Station, which orbits Earth at 400 kilometers altitude and is close enough that a rescue mission can be launched in an emergency within hours, the Gateway at its farthest point is more than 70,000 kilometers from the lunar surface and more than 300,000 kilometers from Earth. There is no quick rescue from the Gateway. There is no quick anything from the Gateway. Everything about it is defined by its isolation. The Gateway exists because of a fundamental constraint of human deep space operations. You cannot launch a direct mission from Earth to the moon's surface every time you want to change the crew. A direct Earth to Moon to Earth mission, of the kind the Apollo program flew, is extraordinarily expensive in propellant and therefore in launch mass and therefore in cost. Every Apollo mission required a Saturn V rocket, the largest and most powerful operational rocket in history, to launch a spacecraft capable of carrying 3 astronauts to the moon and back. The Artemis program, using the Space Launch System and commercial landers, faces similar fundamental mass constraints. Direct return flights are possible but costly. They are not the model for a base that needs continuous resupply and crew rotation. The Gateway model works differently. An Orion spacecraft launches from Earth, rendezvous with the Gateway in lunar orbit, transfers crew and cargo to a smaller lunar lander. The lander descends to the surface, and when crew rotation time comes, the process reverses. The lander can be refueled from propellant stored at the Gateway or at the surface. The Orion spacecraft, instead of having to carry enough propellant for the entire round trip, only has to carry enough for the Earth to Gateway and Gateway to Earth legs, which are significantly less demanding. The Gateway acts as an intermediate waypoint, a fuel depot, a communications relay, a command center, and a safe harbor where a crew in trouble on the surface can be recovered to a pressurized habitat while rescue options are organized. The Gateway also carries a scientific laboratory and crew quarters for a crew of 4, though NASA has been explicit that the Gateway is not intended to have crew aboard continuously. It will be occupied during lunar surface missions and for periods of maintenance and scientific operations, but it will spend stretches of time unscrewed, operating autonomously with its systems maintained remotely from Earth. In this sense, it is less like a space station and more like a lighthouse that people visit to keep working. automated when no one is there, inhabited when the mission requires it. The first elements of the gateway, the power and propulsion element, and the habitation and logistics outpost, are scheduled for launch in 2027 and 2028 respectively, aboard commercial rockets. By the time the first Artemis crew lands at the South Pole in early 2028, the gateway will already be in orbit, waiting for them. By 2033, when the permanent base begins continuous occupation, the gateway will have been operational for 5 years, its systems tested and proven, its role in the overall architecture well understood. From the gateway's windows, if you are there to look, you see two things. You see the moon below you, close enough during the orbital passes to make out individual craters and ridges, a world of gray and shadow, and the occasional glint of a solar panel or a habitat dome at the South Pole, alive in a way it has never been before. And you see, when the orbit carries you far out, the Earth, blue and white and impossibly beautiful and impossibly small, hanging in blackness at a distance of more than 300,000 kilometers. The people on the gateway can cover the entire Earth with their thumb. Every person they have ever known, every city, every ocean, every weather system, the entirety of human civilization fits behind a human thumb from where they are standing. Let's be explicit about what this combination of systems actually achieves. By 2033, the design calls for a self-sustaining human outpost on another world, not supported by Earth, not supplied by a chain of cargo missions arriving every few months with air and water and food. Self-sustaining. Water extracted from the ice in the craters, oxygen produced from that water by electrolysis, hydrogen produced by the same process and stored as propellant, food grown in pressurized greenhouses using hydroponic systems that recycle their own water and nutrients, energy generated by nuclear fission from uranium fuel that was brought from Earth but that will not need to be replaced for a decade. The base will still be connected to Earth. People will still travel to and from it. Scientific data will still flow back to Earth in enormous quantities, but it will not need Earth in the same moment-to-moment way that the International Space Station does, where a resupply mission arriving late is not an inconvenience, but a potential emergency. The International Space Station consumes roughly 900 kilograms of food per year per crew member, all of it launched from Earth. It requires approximately 7,000 kilograms of cargo delivered annually to maintain operations. Every kilogram of that cargo costs money to launch. The Artemis base, in its target configuration for 2033, aims to produce enough water, oxygen, and food supplements locally to reduce the required Earth-to-Moon cargo mass by at minimum 50% compared to an equivalent station approach. The economic significance of that reduction is not abstract. It is the difference between a program that requires continuous massive expenditure to sustain and a program that becomes progressively cheaper per unit of capability as local production scales up. It is the difference between a base and a colony. The engineers who are designing these systems know what they are building. They know that the fission reactor buried in the regolith and the water extraction equipment drilling into the polar ice and the regolith printed walls of the habitats are not just solutions to immediate logistical problems. They are the prototype for something much larger. They are the proof that it can be done. They are the demonstration that a species born on one world can survive on another. And they are the infrastructure, the very literal physical infrastructure, that will make it possible to do on Mars what is being done on the Moon. Everything being tested at the South Pole of the Moon in the 2033 to 2040 period is a Mars mission in miniature. The fission reactor is a smaller version of what Mars will need. The water ice extraction technology is the same basic technique that will be used to extract water ice from the Martian subsurface, where it is known to exist in enormous quantities. The regolith sintering construction methods will work on Martian soil. which has different chemical composition but the same fundamental lack of manufactured building materials. The life support systems that keep people alive in the vacuum of the moon will keep them alive in the thin carbon dioxide atmosphere of Mars. The gateway architecture in lunar orbit is the functional template for whatever transit hub will eventually orbit Mars. The moon is not the destination. It never was. The moon is the classroom, the testing ground, the shakedown cruise for the most consequential journey in human history. And 2033 is when the first class begins. You understand now how the base will be built and where it will be located and how it will be powered and how it will be connected to Earth and why it is designed to be self-sustaining. What remains and what no one who has not lived through it truly can understand is what it does to a human being to actually live there, what it does to a body, what it does to a mind, what it does to a person's sense of who and what they are. There is a thought that tends to arrive during the third or fourth week on the International Space Station, according to nearly every astronaut who has spent extended time there and been willing to talk about it honestly. It does not arrive when you first see the Earth from orbit and feel the famous overview effect, the sudden, overwhelming sense of the planet's beauty and fragility and wholeness. That comes early, often on the first day, and it is intense and wonderful. The thought that comes later in the third or fourth week is different. It is quieter. It is the thought, hard to articulate and harder to push away once it has arrived, that the blue marble below you is getting smaller. Not physically. You are at a stable altitude, the same 400 kilometers above the surface as always. But psychologically, it is getting smaller. The connection to it feels less immediate. The urgency of everything that happens there feels less urgent. You are still linked to it by radio and video and the knowledge that your family is there and that you will return to it in a few months. But it is starting to seem, despite everything, a little far away. On the Artemis base, that thought will arrive differently, and it will not go away. From the south pole of the moon, the Earth is visible in the sky nearly continuously. A sphere roughly twice the angular diameter of the full moon as seen from Earth, blue and white and brown depending on which hemisphere is facing you, slowly rotating so that different parts of the planet present themselves over the course of a day. It is beautiful. Every human being who has photographed the Earth from space has produced images of heartbreaking loveliness, and the view from the lunar surface is among the most moving in our species' limited portfolio of off-world vantage points. The iconic photograph taken by Apollo 8 astronaut William Anders in December of 1968, known as Earthrise, the image of the blue and white Earth rising above the barren gray lunar horizon, is consistently ranked among the most influential photographs in history. It changed the way humanity thought about its home planet. It gave the environmental movement a visual symbol and a philosophical argument. Simultaneously, here is your world, small and bright and alone, hanging in darkness, and there is nothing like it anywhere you can see. The crew of the 2033 Artemis base will see their own Earthrise every day. They will see the Earth as their context and their home, and, for months at a time, the place they cannot reach. They will cover it with their thumb and know that everything they have ever known is behind that thumbnail. They will watch weather systems build and dissipate over oceans they have swum in. They will be able to see, on a good clear night from the right angle, the faint smear of city lights on the night side of the planet, which means they can see that people are there, that civilization continues, that the lights are still on, and then they will go inside and eat their meal and prepare for the next day's work and lie down in a space roughly the size of a large closet, and they will be 240,000 miles from everything and everyone they love, with no way to get home that is less than days away, and a communication delay that means a conversation with a family member is a series of exchanges, rather than a real-time connection, and a body that is, with every passing day, changing in ways that the people on Earth will never experience. because the moon is doing something to them that cannot be undone quickly. The human body was built on Earth. More precisely, the human body was built by 400 million years of vertebrate evolution in a gravitational field of 9.8 meters per second squared. Every system in the body, from the architecture of the skeleton to the behavior of the cardiovascular system, to the distribution of fluid in the tissues, to the density of the bones, to the mass of the muscles, is calibrated for 1g, Earth's gravity. The body knows 1g. It has spent 400 million years learning to function in it. When you remove it, the body does not simply continue to function normally in the absence of gravitational load. It adapts, it adjusts, it rewrites itself, because evolution built into the body a remarkable ability to economize, and gravity, for the first time in 400 million years, is no longer a load that needs to be carried. On the International Space Station in the zero gravity of low Earth orbit, the changes begin within hours. Fluid that normally pools in the lower body, held there by gravity, redistributes upward. Astronauts' faces puff slightly, their legs thin. The sensation is often described as a persistent mild head cold. The spine decompresses because the vertebral discs, normally compressed by the weight of the body above them, expand when that load is removed. Most astronauts gain between 2 and 3 centimeters in height during a 6-month mission. The bones begin losing density because the skeleton no longer needs to bear full gravitational load, and bone-building cells, osteoblasts, become less active relative to bone-destroying cells, osteoclasts. After 6 months in orbit, bone density in the hip and spine has typically declined by 1 to 2%. After a year, the losses are more significant. Scott Kelly, who spent 340 days on the ISS, returned with measurable changes to his cardiovascular function, his vision, his gene expression, and his bone density. His twin brother Mark, who stayed on Earth, showed none of these changes. The difference was gravity. The moon has gravity. 1/6 of Earth's. Not zero, but not enough. The body's adaptation to 1/6 gravity is not as dramatic as adaptation to weightlessness, but it moves in the same direction. The skeleton still carries some load, but much less than on Earth. Muscle mass still supports some weight, but far less. The cardiovascular system still has to pump blood against some gravitational gradient, but a much shallower one. The specific changes are less well studied than zero-gravity adaptation, because no human being has ever spent more than 3 days on the lunar surface. But the physics and physiology strongly suggest that long-term habitation at 1/6 gravity will produce significant changes in bone density, muscle mass, and cardiovascular function, at rates slower than zero gravity but cumulative over months and years. After 6 months on the moon, a crew member will have lost muscle mass in their legs, back, and core that will require months of intensive rehabilitation on Earth to recover. Their bone density will have declined in the load-bearing skeleton. Their cardiovascular fitness will have deteriorated because their heart has not had to work as hard to maintain blood pressure against a gravitational gradient. These are recoverable changes for a 6-month or even a 12-month mission, provided the crew exercises rigorously during their time on the base and undergoes intensive rehabilitation afterward. NASA learned this from the ISS program and built the exercise protocols and rehabilitation infrastructure accordingly. A crew that does their daily exercise regimen on the moon will come back in worse shape than they left, but in shape they can recover from. But now consider something that the architects of the 2033 base have been careful not to say too loudly, because the implications are ethically and philosophically complex in ways that no policy document has yet fully addressed. Consider what happens not to a crew member who stays for 6 months, but to a person who was born on the moon. The first generation of Artemis base residents will all be adults who grew up on Earth. They will have Earth-calibrated bodies that began their lunar adaptation from a baseline of full terrestrial development. But the base is designed to be permanent. If it is permanent, people will eventually stay not for months, but for years. And if people stay for years, and if the base grows to the scale NASA projects for the 2035 to 2040 period, which includes provisions for expanded crew and potentially for family accommodation in the long term, then at some point the question ceases to be hypothetical. Children will be born in the lower gravity of the moon, and those children will be different, not metaphorically, physically. A human skeleton grows in response to the mechanical loads placed on it during development. Bones grow denser and stronger in the directions they are stressed. Muscles grow larger in proportion to the work they perform. The cardiovascular system develops capacity proportional to the demands placed on it. A child growing up in 1/6 gravity will develop a skeleton that is optimized for 1/6 gravity, with bones less dense than an Earth child's, with a cardiovascular system less powerful, with muscles adapted to a gravitational environment that does not exist anywhere else in the entire inner solar system except at one location, the surface of the moon. Such a person, in the current projections of lunar physiologists, could almost certainly not return to Earth. Not easily. Perhaps not at all. Earth's gravity, which every human being who has ever lived was born to carry, would feel to a moon-born person like wearing a suit of lead every moment of every day. Their spine, their hip joints, their cardiovascular system were not built for it. Moving in Earth's gravitational field would be painful, exhausting, and potentially dangerous. They would be, physically, a different kind of human being. Adapted to the moon, maladapted to the Earth. This is not science fiction speculation. The physiological mechanism is straightforward and well understood. The question is not whether it will happen, but when, and what it means when it does. Because the first moon-born human child will be, in a way that no legal or philosophical framework currently exists to address, not an Earthling. They will have been born on another world. They will carry within them the evolutionary legacy of 400 million years of terrestrial life. But they will have spent their developmental years under a different sky, in a different gravity, in a different light, in a world where the horizon is closer and the Earth is always visible above it, and the stars never twinkle because there is no atmosphere to make them do so. What will they think when they look at Earth in the sky above the moon? Not the way the astronauts think, who grew up there and left it. They will look at Earth the way someone looks at a place they have only ever seen in photographs, a place their parents came from, a place in the history books, a place that contains most of the human species and most of human culture, and the entire natural world, and the oceans and the forests and the weather. But a place that they cannot go, a place that, for them, is not home, a place that is, in the most precise possible sense of the word, foreign. This is what NASA calls the human factors challenge of long-duration lunar habitation, and the language is admirably calm for the enormity of what it is describing. Every long-duration space mission involves significant psychological challenges: isolation, confinement, the loss of access to natural environments, the disruption of normal social connections, the stress of living and working in close proximity with the same small group of people for months. These challenges are well documented on the ISS and in Antarctic winter-over stations, which are the closest Earth analog to a permanent lunar base. The people who winter over at places like Concordia Station in Antarctica, which runs on 24-hour darkness for about 4 months of the year and is inaccessible to the outside world for roughly 9 months, exhibit measurable changes in neurological function, including reduced cognitive performance, altered sleep patterns, and emotional blunting that researchers believe is an adaptive response to monotonous and confined environments. If they are experiencing this at a station on Earth with natural gravity and emergency evacuation options, and the ability to communicate in real time with anyone on the planet, what will it be like on the Moon? The distance to Earth from the lunar surface is, in communications terms, only 1 to 3 seconds. A light speed delay that is barely perceptible in text exchanges and only mildly disruptive in video calls. But the psychological distance is another matter. The Apollo astronauts, who were on or near the Moon for a matter of days, uniformly described the experience as one of the most profound of their lives. But they were also counting down to their return from the moment they arrived. For a permanent base crew on a 6-month rotation, the return is not imminent. For a crew on a year-long rotation, the return is a distant future event. For a crew with no fixed return date, because they are the permanent staff of a facility that does not stop operations, the return may not come at all for years. Michael Collins, who orbited the Moon alone in the Columbia Command Module, while Armstrong and Aldrin were on the surface during Apollo 11, was alone for the 47 minutes of each orbit when Columbia passed behind the Moon and was cut off from all radio communication with Earth, a period of isolation more complete than any other human being had ever experienced. Cut off from all of humanity by the mass of the Moon between him and every other person who had ever lived, he described it as not lonely but rather as solitary and serene. But he was alone for 47 minutes, knowing that in 47 minutes he would emerge from behind the Moon and his radio would work again, and his 2 colleagues would be there, and in 3 more days he would be home. The crew of the 2033 Artemis base will not have that 47-minute horizon. They will have days and weeks and months. The Moon will not pass between them and Earth, but it will be there, enormous, present, unchanging, defining the boundaries of their world. NASA's Behavioral Health Research Program, funded at significantly higher levels since 2020, has developed sophisticated screening protocols to identify candidates who are likely to perform well psychologically in isolated and confined environments for extended periods. They have developed communication protocols, scheduling guidelines, and privacy norms informed by Antarctic winter-over data and the ISS experience. They have developed therapeutic support frameworks that provide crew members with access to professional psychological support via communications link. They have developed a concept called autonomous behavioral health maintenance, which is the jargon-heavy way of saying that the crew will have tools to monitor their own psychological state and intervene before small problems become large ones. Because on the Moon there is no one you can call to come help in person. There is another element to the psychological challenge that rarely gets discussed in the official mission planning documents, because it is harder to quantify and harder to plan for. It is the element of meaning. On the International Space Station, crew members can see the familiar geography of the Earth below them on every orbit, the shapes of continents they have driven across, the coastlines they have walked along. The visual connection to the world they came from is continuous and detailed. On the Moon, the Earth is visible, but it is small. It does not show you the highway you drove on yesterday. It shows you the hemisphere. North America might be in sunlight or it might be in shadow. The city where your family lives is invisible, a dot lost in the continental geometry that you have to imagine rather than see. The connection is there, but it is abstract in a way that the ISS experience is not. You are not looking down at your world. You are looking across at your world, from a distance that requires an effort of imagination to bridge. The crews who have spent the longest time in the most isolated environments on Earth, the winter over teams at places like Concordia Station in Antarctica, describe something that researchers call third quarter phenomenon, a dramatic drop in morale and cognitive performance that tends to occur not at the halfway point of a mission, but in the period roughly 3/4 of the way through, when the excitement of arrival has long since faded and the relief of departure is not yet close enough to provide motivation. On a 6-month mission to the Moon, The third quarter falls at around the 4-month mark. In the deep middle of an experience with no weekends, no change of scenery, no natural environment, no weather except the artificial atmosphere of the habitat, no sunrise or sunset at normal intervals because the lunar day and night cycle is nearly 30 times longer than Earth's. The light outside does not change on a human timescale. The gray surface outside the window looks exactly the same at month 4 as it looked at month 1. Understanding this in advance and building mission structures that counteract it is one of the more important and less celebrated engineering challenges of the Artemis space program. The solution is not just psychological, it is architectural. Base designers are specifically incorporating natural spectrum lighting systems that cycle on human timescales to simulate sunrise and sunset. Even though no such cycle exists on the lunar surface, they are incorporating access to growing spaces, areas where plants under artificial light produce some portion of the crew's food and produce oxygen as a byproduct, partly because growing things produces useful nutrition and oxygen, and partly because growing things provides the crew with something living and changing and responsive to care in an environment where everything else is either mechanical or geological, and neither requires nor responds to human attention. They are incorporating dedicated private spaces, not just common areas, because the research on Antarctic winter over makes it unambiguous that regular, guaranteed solitude is not a luxury for people in confined environments, but a psychological necessity. And they are incorporating what mission planners somewhat clinically call meaningful mission tasks, which is the research-backed recognition that people in difficult environments tolerate the difficulty better when the work they are doing seems important. On the moon, that is not a hard case to make. All of this is necessary. All of it is real, and all of it together is still not an answer to the deepest version of the question, which is not how we protect the astronauts' mental health on the 2033 base, but what it means for the definition of humanity when the moon is no longer a place people visit and return from, but a place people live. The philosopher William James once wrote that the greatest revolution of our generation is the discovery that human beings, by changing the inner attitudes of their minds, can change the outer aspects of their lives. He was not writing about space travel. He was writing about psychology. But his words describe something true about what the permanent lunar base will do to the human beings who inhabit it. The Artemis space crew will change, not just physically, but in their inner attitudes, in what feels normal, in what feels like home. The gray surface outside the habitat window will become familiar. The earth and the sky above will become the distant thing, the exotic sight, the reminder of where they came from, rather than where they are. The silence of the moon, which is total and absolute in a way that no place on earth can match, will become the background of their existence. The sound of their own breathing in a pressurized suit, the hiss of the air recycling system, the low hum of the fission reactor a kilometer away. These will be the sounds of their world, and slowly, gradually, over months and years, the moon will stop being a place they are visiting and start being a place they are from. This is the moment that the Artemis program was always building toward, whether or not its planners said so explicitly. The technical goals, the water ice extraction, and the fission power, and the regolith printed habitats, and the gateway in the Mars springboard timeline, all of these exist in service of a deeper transformation, a transformation in the relationship between our species and the universe that contains it. The moon base is not the end of the Artemis program. It is not even the end of the chapter. It is the first sentence of a story that will take centuries to tell. The road to Mars runs through the lunar South Pole. This is not poetic language. It is engineering fact. A human mission to Mars requires propellant. Enormous quantities of propellant. A spacecraft capable of carrying 6 crew members to Mars and back, depending on the architecture, requires somewhere between 150,000 and 300,000 kilograms of propellant for the transit alone. not counting the propellant for landing and departure from the Martian surface. This is far more than any existing or planned rocket can deliver to Mars in a single launch, which means either the propellant must be produced in space, or the mission must be assembled from many launches, or both. The lunar water ice extraction infrastructure, once operational, produces hydrogen and oxygen that can be stored as cryogenic liquids, liquefied hydrogen and liquefied oxygen, in tanks at the lunar base or in the gateway. A spacecraft departing for Mars from lunar orbit, fueled by propellant produced from lunar water ice, does not have to carry that propellant up from the bottom of Earth's gravity well. It starts from the Moon, which has 1/6 of Earth's gravity. The difference in energy required to reach Mars from low lunar orbit versus from low Earth orbit is significant, reducing the total launch mass required for the mission by roughly a factor of 4. The 2033 to 2035 window, the favorable Mars launch window that makes the 2033 date significant, is now legible in its full meaning. It is not enough to have a spacecraft ready for the Mars window. You need the propellant to be there. You need the infrastructure to produce the propellant to have been running long enough to have filled the tanks. You need the crew who is going to fly to Mars to have spent time on the Moon, adapting to partial gravity, testing the life support systems that will sustain them for 9 months in transit, learning how to live in a hermetically sealed artificial environment with no resupply option, and no ability to turn back once a certain point in the journey has been passed. Every one of those requirements points back to the same date, the same facility, the same infrastructure that must be operational and proven before the Mars window opens. The 2033 moon base is not the end. It is the launch pad. Not metaphorically. Literally. Think about what the person standing on the lunar surface in 2040 will be able to see if they know where to look. They will see Earth, as always, in the sky above them. They will see the gateway in its halo orbit passing overhead, perhaps lit by sunlight, a small bright point moving faster than a satellite crosses the Earth's sky. They will see, in memory and in the records they carry, the images of what the South Polar regolith looked like in 2028, before the first structures were built, before the first drill went into the permafrost, before the first reactor went online. A place so unchanged that the tracks of an ancient meteorite impact were still crisp in the regolith after billions of years, and they will see around them what that place has become. A base, a settlement, a piece of infrastructure as permanent as any human construction, as permanent as a dam or a road or a bridge, something that will be there in 100 years and in 1,000 years and perhaps in 10,000 years. Long after the humans who built it are gone, the footprints of the Apollo astronauts are still there, somewhere to the north and east, preserved in the airless silence of the Mare Tranquillitatis. They will be there for 1,000,000 years. The tracks left by the rovers of the Artemis base, the boot prints of the astronauts who built it, the excavations and structures and cables and antenna arrays, these too will persist. They will outlast the specific humans who made them. They will outlast the institutions that funded them. They will outlast the names and the nations and the political systems that decided to build them. They will be there when the sun has brightened enough that it begins to boil off Earth's oceans, a process that will begin in roughly 1 billion years. They will be there, preserved in the vacuum, in the cold, in the silence. For 4 billion years, the moon kept perfect silence. In 2033, that silence will end, not with a short visit, but with people who have come to stay. The first permanent human settlement beyond Earth will begin its work. Lights will shine on the lunar South Pole, and the gray, airless world that once preserved only footprints will now preserve something far more powerful, the sound of humans living. The Artemis base, when it opens its habitats to the first long-duration crew in 2033, will not look like the science fiction we grew up with. It will not be gleaming and white and elegant. It will be gray and cramped and covered in dust in places where the dust mitigation systems have not quite worked as planned. It will smell slightly of burned gunpowder and recycled air and whatever the hydroponic system is currently growing. It will have a wait list of scientists and engineers who desperately want to go there. It will have a maintenance backlog. It will have a communication system that lags by 2 seconds and a medical bay that is excellent by off-world standards and concerning by Earth standards, and a nuclear reactor humming quietly a kilometer away in the dark. It will be unglamorous and demanding and expensive and sometimes frightening and sometimes beautiful, and it will be real, and it will be ours. And it will be the first place our species has ever truly lived beyond the blue marble of the world that made us. The Earth, seen from the Artemis base, is a marble you can cover with your thumb. Everything that has ever happened to any human being who has ever lived fits behind that thumbnail. Every war and every love story and every scientific breakthrough and every painting and every piece of music and every moment of grief and every moment of joy. Covered by a thumb, held in a sky above a gray, airless, silent world where 12 human beings once walked and left footprints that will never erode. And now, for the first time in 4 billion years, there are lights on.